This lesson is going to be looking at the different types of numbers and families that we have in math. The first type of two numbers that I want to look at are numbers that you first learned very long ago in elementary school. Those are the two basic types of numbers we have. We have even numbers. Those are numbers that end in the numbers 0, 2, 4, 6, or 8. Or we have odd numbers, which are the other numbers, or the numbers that end in 1, 3, 5, 7, or 9. These next two numbers are a little more advanced, and they come from the activity that we did in class. So the first type of number is a prime number. Prime numbers are the numbers from the chart that only had one rectangle, which means that they only had two numbers that could multiply together to get that number. So they only have two factors. And those two factors specifically are 1 and itself. For example, the only way you can get 5 by making a box is by having one side be 1 and the other side be 5, because the only multiplication problem that equals 5 is 1 times 5. The other type of number is a composite number. Composite numbers were the numbers on the chart that had more than one rectangle. So, for example, number 6 is a composite number because composite numbers have more than two factors. You could make more than two, or you can make two or more of those rectangles. So the first rectangle you see pictured is a 1 by 6, where the other one is a 2 by 3. So the factors of 6 are 1, 2, 3, and 6. Now we're getting into the little bit of the 8th grade relationships of numbers. So the first type of number that we're looking at in this sense is real numbers. Real numbers are any numbers that can be placed on the number line. For everything that we do in this class, every number that we take a look at, no matter what it is always going to be considered a real number. So if you're ever asked to identify what family a number belongs to, in our case, it will always be a real number. The next type of number that we're going to take a look at is irrational numbers. Irrational numbers are those numbers that cannot be written as a fraction. The examples of irrational numbers are pi. Pi is approximately 3.14, but however, that's an approximation. The actual number of pi is an irrational number, as it cannot be written as a fraction. You can also have decimals that are irrational decimals, or irrational numbers as well. Irrational decimals are non-repeating and non-terminating decimals. So I could have something like non-repeating means that the numbers don't repeat in a pattern, and terminating means to stop. So a non-repeating and non-terminating decimal could be like, I don't know, 0.1, 2, 3, 4, 5, 6. There's no pattern to that. And then those three little dots at the end tell you that the number keeps on repeating. The next type of number we could have would be rational numbers. Numbers that are rational are numbers that can be written as a fraction. So a fraction, hopefully, obviously, can be written as a fraction. An integer can be written as a fraction, which we'll talk about what an integer is in a minute. Terminating decimals, again, terminating means decimals that stop. So I could say, for example, 0.5. 0.5 or 1/2 is a terminating decimal. I could also say repeating decimal. So I could say 0.55555, or I could say 0.5 with the bar over top. The bar over top insinuates that it repeats. And then square roots of perfect squares. Square root is a symbol that looks like a division sign, and if you have a perfect square like 25 underneath it, that's asking you what number times itself gives you the number underneath the square root sign. So I could say what number times itself is equal to 25. Well, I know that 5 times itself is equal to 25, so the square root of 25 is equal to 5, which is a number that can be written as a fraction. We will talk more in an upcoming lesson about what square roots are and how to find them. The next type of number is integers. Integers are all whole numbers and their opposites. So I could say 3. The opposite of 3 would be -3. I could say -7. The opposite of -7 is 7. 0 is also considered to be an integer. The next type of numbers are whole numbers. Whole numbers are the numbers you count with, except those, this time they begin at 0. So my whole numbers, nothing smaller than 0, and they're my whole numbers, meaning they don't have any fraction or decimal parts. So I would have 0, 1, 2, 3, 4, 5, etc. The last type of set of numbers is natural numbers. Natural numbers are counting numbers that begin at 1. So this time they don't include 0. So I would have 1, 2, 3, 4, 5, 6, etc. Now I want to take a look at something a minute before we finish with the types of numbers. You will be given a diagram that looks sort of like this that we have filled in class regarding the number families. Here's first another example that doesn't include number families so that you understand, first of all, how to read the chart. So let's say over the weekend you witnessed somebody breaking into the school. Okay, so let's say Miss Willis pulls you aside and says, hey, can you tell me what you know? You might not really want to rat out your friend or somebody you know, so you want to give her clues to see if she can come up with who the person who broke into the school is. So one of the most general things that you could say would be that the person is a student at CCSD. Okay, that narrows it down, right? That takes out people like your mom, your dad. There's students who maybe are visiting Las Vegas, but that doesn't limit those of who could be, because there are a lot of students who are actually attending CCSD. Then you could say that, I don't know, if you want to be a little more specific, you could say that it is a Bridger student. Oops. Okay, it's a Bridger student. So how we're reading this diagram so far is the big rectangle consists of CCSD. The rectangle that has the word Bridger in it represents all of Bridger's students. Bridger's students, or all of Bridger's rectangle, is inside of the rectangle for CCSD because Bridger is a part of CCSD. Now, if I said the student went to Von Tobel, right, I cannot put Von Tobel in the same box as Bridger. Von Tobel would have to go over on its own side. Okay, Von Tobel is still part of CCSD, so it's still in CCSD's rectangle, but it is not in Bridger's rectangle. So let's say now Miss Willis says, okay, it's somebody who is a student at Bridger. I need a little more than that. Well, you could go a little more specific, and you could tell Miss Willis that it is an 8th grader. So now that limits, right? And that limits those of them that could be the suspects. It takes away the 6th graders and the 7th graders. The 8th grader box is inside Bridger's box because all 8th graders at our school attend Bridger. And they're also in the CCSD box because you are all CCSD students. Then let's say you want to get a little more specific. So let's say now you say that the student is not only an 8th grader, but they are on the Merlin house. That would limit 2/3 of the 8th graders away, as only 1/3 of our 8th graders are in Merlin. If you wanted to go even more specific than that, you could even tell them that they have me as a math teacher, right? Notice my box is inside the Merlin box because I'm a member of the Merlin house. My box is inside the 8th grader because the 8th grader is a member of Merlin and in my class. And then it's inside of the Bridger box because anybody in my class goes to Bridger, and then anybody in my class goes to CCSD. So if I said I wanted to consider one of you, if we're looking at you right now, would be in this box because you are in my class. You're not necessarily a member of Merlin, but let's pretend for the sake of argument that you are. So I have me in there. I could ask, are you a member of Von Tobel? No, because your little dot is not inside the Von Tobel box. Now let's say, okay, you are friends with somebody who has Miss Bassett for math. If they have Miss Bassett, they could still be a Merlin, right? But they would be outside here. So if I'm talking about this blue dot, I can say that the blue dot is not in Miss Van Leer's class. However, they are part of Merlin because they're in the Merlin box. They are an 8th grader because they're still in the 8th grade box. They go to Bridger because they're in the Bridger box. And they attend CCSD because it's still in the CCSD box. So now that we understand a little bit about how to read that diagram, I want to take a look at this diagram. Same diagram, except now this is the diagram that we created in class. So if we're looking at the largest box being the real numbers, then we have kind of a separation. Numbers can either be rational, which remember means they can be written as a fraction, or they can be irrational, which means they cannot be written as a fraction. The irrational box is kind of left alone, just like the Von Tobel box was on our example. Then we have other boxes that are smaller groups inside the rational box. We have the integers, then the whole numbers, and then the natural. So could I be an integer and still be considered a whole number? Absolutely. Because whole numbers, some of them are in the integer box. Could I be a natural number and be an irrational number? The answer is no, because there is no natural box inside of the irrational box. Could I be a real number and be an integer? The answer is yes, because an integer is part of the real number box.